So, a horrible assassination was conducted, attempted to me. The buffet is closed and there is no cafe. The machine works only with points. So my productivity will be decreased in the next 15 minutes, seriously. Okay, so practice. Actually I start earlier, but I start because then we have more time to do exercises. Yes, where we are? We are here. This is a very similar to the previous stuff. The difference is that now I have the exercises. Last time, sorry, you had exercises in Hungarian, so I had to write on the board and translate. It was not perfect. So we had done this, which is a bit in medias res, but doesn't matter, at least we have done and we have moved on. Next one is this one. So we finished the first three. No, the first four. First four. Yes, the four, that was the last. Great. Okay. Great. So now we have English exercise. Metal surface is radiated, illuminated. Illumination means, well, something reaching the nirvana or something like this, but I don't know. Is illuminated by or radiated by light of wavelength 492 nanometers. The maximum kinetic energy of the emitted electrons is this one. When the wavelength of light is changed to this, the kinetic energy decreases to this one. Based on these data, determine the constant and the work function characteristic of the metal. Great. Yeah. I started earlier. Where did you take this, the candy, the water? The buffet is closed. I don't know the place. So where can I take coffee if that buffet is closed? So where did you take your candies and water?
There is the showdowns
Okay. So it's something different. Doesn't matter, not important. Not physics. Okay, so now what I told you is that last time, I must apologize, last time you had Hungarian exercises. I translated them to English. That will be available on the module and also on GitHub. And now we continue with the last two exercises. So, first thing to understand what is the task. So you have a metal surface. You have photon and one electron escapes. Out. Second, we have the same method. You have a different photon, and the electron is a different escape. Kinetic energy. says the energy characteristic of the metal, but, well, we will see. So what we know, first of all, the first case, you have this 492 nanometers. It's something green light or something like this. The other, this 579 nanometers, is something yellow. So the first case, the wavelength is shorter, the frequency is higher, and the energy of the photon is also higher. And what you can see is that in the first case, the electron, when it escapes, has higher energy than this one, than here. This is almost 20 times higher in that case. So this is good. Seems to be reasonably good, this exercise, and more or less now we understand it. At least me. But I hope you also. No, I'm believer. You know, Friedrich the Great said that the hope means the hope is the first sign of you are defeated, or something like that. It's not perfect. So we have energy usually. We have frequency. We have the photon energy. That's this. No, it's better. So we have the energy of the photon, and this will be some threshold from the metal, and the kinetic energy. This is the Planck constant times frequency, and this is the metal, and also we have this kinetic energy. We don't have frequency, we have wavelength. So we have we don't have mirrors. Okay, so this is the key equation. Everything that we know. We know the kinetic energy. We know the lambda, the wavelength, and what is the name? The speed of light. We have Planck constant. We have speed of light. We have lambda 1. We have this mystic stuff of the metal. And we have the kinetic energy of the electron. And we have this twice. So, determine this EM and the Planck constant. First, subtract the second decoration from the first one. So I will have something like this will disappear. Okay, we know lambda 1, lambda 2, we know the energies, we know the, what is the name, speed of light. So we can determine the Planck constant. R revolutionary RV. So H is
6.626 equals to 10 in the minus 34.
You have calculated already?
No, it is the Planck's constant. You use this? The constant value.
Sorry,
You use the constant value?
you determine that constant value.
Yes, that H.
No. That's the exercise, the task.
We need to calculate this now.
Yes.
It's not constant.
Yes. It's constant, but we don't know. We are revolutionary experimental physicists and we determine the Planck constant right now. It's okay, thank you. Okay, I forgot to do something. Nanometer is very nice, but we don't like the heat. Meter is our friend. The joule is fine. That's okay. I'm quite happy with the joule. So, let's see what we have here. Lot of mess. This is okay, let's see what we have. Okay, the unit, okay, I have private students, pupils, and one of them just told me he has never seen anyone who cooperated with the units. Well, I made a lot of mistakes, so I have some methods to check myself. Here we have Joule. There is meter per seconds per meter. So the unit of the result will be Joule seconds in the Planck constant. That's fine, that's okay. So this works. And this is not 6. Oh. Okay. This is 0, so this is 20 minus 10. Let's see what we have. We have something that's quite interesting. This is very, very interesting. So this will be 9, 20, okay, interesting. So what we have, Joule second is the unit, and based on the numbers, it's something. This is the order, because that's minus 9, that will be plus 9, and then divide, so it's okay. Oh, I forgot something. Yes, I forgot something. 20. Oh. This is interesting. What was the value of the Planck constant? 6.62, and then 10 on the minus 34. Then something is not good, or I don't know, we will see. Is it? I have an idea what is wrong. Not this is wrong. No. So it's minus 9. Oh no, it's okay. Minus 9, that's plus 9, 17. Okay, so this is not that one. Okay, it's better. So let's see what we have. perfect, but much better. That's R Planck constant. Of course, it's not that one that is in the books because we have these numbers. So perhaps it's wrong, and actually always it's difficult to determine these values. Fine. Seems to be this calculation good. So we have the Planck constant, and now we need this metal energy characteristic. No. We know the Planck constant, we know the speed of light, we know the wavelength, we know the kinetic energy. So we can do it easily or not. So, we have everything that we need. So this A is nothing more than okay, so this Ah, great. Okay, so it means so this is the energy that's necessary to leave the metal. Well, these are their numbers. We have 20 minutes. So, we can do the following. This is ready. Okay. However, there is an alternative method. The other energy and wavelength. screen. I got the same number, but it's different with the order of magnitude. Yes. Yes, because that's wrong. It's minus 27, and then it's minus. Okay, great. So we got the same. Here, there's a miscalculation. Here, this is the end of the task. This is just check. It is not necessary to do, just I was not sure that I am right. Do you understand what we have done? It's the same. So we have a photon, we have a threshold in the metal, and then we can calculate the kinetic energy. It's the same. Just here we had two equations, and we determined the Planck number and this one. Actually, this Planck number is not good. It's not what is in the reality, but perhaps the numbers are not good. But we calculated well because the result for the metal is good. There is also something that's common. Sign. Okay, so we have enough time for a Cooper test, or fix this last stuff. When light of a certain frequency when a matter surface is radiated by a certain frequency of light, the measured stopping potential of the emitted electrons is 3.9 volts. For light, half of the frequency, the stopping potential is 0.625 volts. Determine the work function and the wavelength of the light. Okay, so these exercises are hard dash. This is my first semester when I teach this subject, so I use the ancestors, the previous tutors or professors' material. For example, now, this exercise is the same like the previous one. The only difference is the following. In the previous one, this one, 5, we use Joule. Here, they are not so, they don't, this exercise doesn't show mercy. We have to use electrovolts. At least at the beginning, so I will change everything to Joule very soon. Okay. I have an empty. Board. Honest. So we like at a certain frequency this metal stuff, I mean surface. We have electrons to hit out or escaping with certain energy. Then it's the same actually. We have same exercise. We have light with another frequency and frequency. Yeah, but we don't know this frequency. And then the electrons are leaving, and we have another yes, so it has some potential to keep them here. And these are different. So what we have? We have we need the wavelength. And the stopping function, I mean, this is the energy. Metal. I don't really understand this question. Huh. Yes. That's interesting. Okay, this is the that's it. That this is what I mean. This potential is necessary to stop the electrons which are escaping. It's easy to determine the energy. It's not that, but the or no, not W. That's multiplying these numbers with by the charge of the electron. And then oh, really? Yes. So we have these energies. We are happy. And what we know, this is the same. So we have an energy of the photon, and this will become something like this. And we have some work on the metal. This one means C lambda. This one means. Okay, so we have this formula, and we have two equations, H C lambda 1 H C lambda 2 the AM is the same. We don't have males anymore, doesn't matter. Escaping. Okay, so it's not good. We have blunt, we have it will not work. Yes, will not work. Okay, this is true, just it's perfectly useless. We have the kinetic energy, that's fine. We have the something important is missing there. For light of half that frequency, something was missing was okay. So this is half of the frequency is a double of the what is the name? The wavelength. So half frequency double wavelength. This is just a moment. So this is half of the frequency. Frequency double wavelength. So it means something is wrong here. So yes, that's wrong. minutes extra, apologize. You can finish this at home. We have the lambda 1, and from the lambda 1, we can determine lambda 2, and also we can determine the energy that necessary to leave the metal. Okay, thank you very much. See you next week. Utána azt kell tenni, hogy szerintem azért a KTXFI2EBNF. Igen, és akkor a második az nem, arra ezt nem tudja. Most lehet, hogy előbb megcsinálva, tehát meglehetősen sok mindent csinálni, most itt a 4 álláson van. Így alakult, úgyhogy ez nagyon jó fizetnek minden. Tehát egy helyen jó fizetnek, csak az csak a Obudától van. Tehát valahogy meg tudom csinálni, az a legjobb hatni. Nem tudom, mutatjuk el. Egyelőre ezek a relativisztik izével, meg a Comptonnal, meg ezekkel most lehet fejni szépen ezt az órát a következő. Na most egyébként felfogom a másodikat majd, a felülről vannak, de hogy ebből a Fermi-Diract akárból mutatjuk, azt nem csinálni fogom. Az plusz. Egyben ezt mondok. Tehát úgy néz ki a dolog, hogy egyben a kettőre, kapnánk, hogy a mélységnek lesz, tehát kapnak egy ZH pontot, meg kapnak egy vizsgapontot, és akkor azt meg lehet dobni ezzel a kettővel. Mert ugye még egy izé van, azt a jövőre nem fogom most már nem fogom megváltozni, jövőre nem lesz, 40%-ot elterjed az alárás. A felét nem tudom a elégségesen. Oké, viszont igen?
Úgy fog kinézni, mint tavaly?
Tessék?
Úgy fog kinézni körülbelül, mint tavaly, Zsóka...
Amit csinál?
A vizsga.
Fogalmas.
Zsóka
Ugyanis én október 1-től vagyok itt, fogalmas, mint hogy a vizsga tavaly.
Igen, most én azért csak elmélet volt.
Tehát lesz egy, nekem én úgy gondolom, azt elmondom az elején, hogy lesz egy ZH, ott feladatot oldanak meg, mindent használnak egymáson meg elérhető eszközökön kívül. Persze számoló, hogy milyen nem lesznek, hogy kitalálnak, hogy csinálni. Zavarom, hogy nem tudom, valahol nem kitalálni. A vizsgán, ott meg elméleti kérdések lesznek, nem fog kérdezni feladatokat. Tehát, vagy hogyha van valami, akkor az elméleti feladat. Rákérdezek fogalmakra, meg hosszabb folyamatokat kell elérni. Mit tudom én, írja le az atomoknak a elektronszerkezetét, és mi a köze a periódikus rendszernek az elemeihez. És akkor erről írnak el egy oldalt, akkor, hogyha van valami köze ahhoz, amit elmondnak, akkor minden boldog leszek, megadom a maximumot.
És akkor ehhez mondjuk ez a kérdés, ezt gondoljuk, akkor két nap volt, a Dörföld atommodell, és azt úgy elmagyarázni, hogy ez mi értelmezés, hogy milyen három dimenzióban.
Igen. Tehát ezt vissza. Vagy, hogy mik ezek a P, meg ezek az N szennyezések. Egyébként csodálkozom, és más szállót használom, csak földolgozom, meg kell fordítani angolra, hogy például nem beszél, nincs benne a dióda, meg a tranzisztor. Ezt bele fogom rakni a vonaton visszafelé résen. Tehát, hogy ez az értelme. De értik, hogy ez egészen mi az értelme? A tárgyal. Most önök tanultak már tranzisztorokról?
Sajnos.
Az minden sajnos. Tehát van elektronikumban, nem? És a Kirchhoff törvények meg a társai. Olyanok voltak az alap.
Igen.
És akkor utána volt ilyen, hogy ilyen...
Utána belevettünk külön félvezetőkbe egy másik tárgyban.
És a félvezetőkről mit tanultak?
A felépítésüket, a karakterisztikát, alkalmazásokat.
Kicsi elméletet, hogy a tanárban magyaráztál, hogy elkérjük a vannak és az elektron átféle.
Ezt én magyaráztam így, vagy az, aki azt a tárgyat tartotta?
Horváth már.
És akkor ő ugyanezt mondta ezeket a igaz dolgokat.
Igen.
Jó, oké. Ez lenne a lényeg egyébként, tehát ez a lyuknak a működik. Majd egyszer valamelyik ők csinálni őket, amit csinálni ingyenesíteket Magyarországon. Jó lenne. Nem?
Jó lenne.
70%-ot a testalajban van. Nagyon szeretnék ezt az országot, nagyon sokan. Minket is szeretnék. Még valami kérdés? Jaj, basszus! Nem kapcsoltam kérdezépen. Menjenek nyugodtan.
Köszönöm szépen.